We have to discuss a new algorithm for finding maximum flow. It is Edmonds-Karp algorithm. What is the difference between Ford-Fulkerson algorithm and Edmonds-Karp algorithm? Fulkerson never specify how to find an augmented path, but Edmonds-Karp algorithm specifies the way you will be finding an augmented path. You have to use breadth first search (BFS) for finding an augmented path, and the breadth first search will give the shortest path from source to sink. So the time complexity will be reduced in Edmonds-Karp maximum flow algorithm. Let us revise depth first search and breadth first search. In Ford-Fulkerson algorithm, you can use BFS or DFS for finding an augmented path. This algorithm is familiar to you. A recursive algorithm for depth first search. We will be making the node visited, then we will find the adjacent nodes. If that adjacent node is not visited, we will perform DFS on that. Let us consider a graph. This is the graph. You are doing a recursive DFS on S. So DFS and BFS, they are algorithms for graph traversal. Graph traversal means how can you reach or visit every node on a graph. Okay, so starting from S, we will be making visited of S equal to true. Then we will be connecting the adjacent vertices of S. We can see A and B are adjacent vertices of S. We are making, let us select A. We are making its visited equal to true. Then selecting adjacent vertices of A, they are C and D. We are picking C, making its visited property true. Now we have visited the nodes in the order first S, then A, then C. C has no adjacent vertices, so we are returning to A. This remember, it is recursion. A has one more adjacent vertex, it was D. Visit D and make it visited property true. D has adjacent vertices G and T. Let us choose G, make it visited property true. G has no adjacent nodes, so return to D. D has one more adjacent node, so visit that, make the visited property true. T has no adjacent vertices, or return to D. D already visited, nothing to do there, return to A. We have visited A, nothing to do there, return to S. S has another adjacent node, it is B. Come to B, make its visited property true, collect the adjacent nodes of B, that is E and F, select E, make its visited property true. E has no adjacent vertices, so return to B. B has one more adjacent vertex, it is F, make its visited property true. It has no adjacent nodes, so return to B. Nothing to do there because we have visited all the adjacent vertices of B. Return to S, nothing to do there, so return. Okay, so we will be visiting the nodes in this order: S, A, C, D, G, T, B, E, F. This is a recursive DFS. Next, let us see the iterative DFS. Let us check what is iterative DFS algorithm. Here we will be using a stack. When we reach a vertex, we will be pushing that vertex to B. Then while stack not empty, we will be popping it out and make it, we will check whether it is visited or not. If it is visited, we will skip that. If that vertex is visited, we will skip that. Otherwise, we will make its visited property true and collect the neighbors. If the neighbor is not visited, we will push it into the stack. We will continue the operation. Once again, once we start at a vertex, we will push that vertex to stack. Stack will not be empty, so this while loop will work. We will pop that item, that vertex, and if the visited property of that vertex is true, we will skip. Otherwise, we will make the visited property true and collect all neighbors of that vertex. If the neighbor is not visited, we will put that neighbor into the stack. We will continue until there are no items in the stack. This is the algorithm. Let us apply this algorithm on this graph. We will start with S. We will push this vertex S to the stack. Then while stack not empty, we will pop that and make it, if it is visited or not. Now its visited property is false. Initially all the nodes, we will set the visited property is equal to false. So now visited property of S is false. We will make its visited property true. Next we will collect the adjacent vertices of S. They are A and B. Since A visited property A is false and B is false, we will put them into the stack. A and B. Then we will pop B. Stack is not empty. We will pop B. So A will be here. And what about the visited property of B? It is false. We will make the visited property true and collect the adjacent vertices of B. Adjacent vertices of B is E and F. We will be pushing them to stack. Since stack not empty, we will continue the iteration. We will pop F. Pop F, make its visited property true. It has no adjacent vertices, so leave it. For the next node, it was E. Make the visited property true. It has no adjacent vertices, so leave it. Then pop A. Pop A. Its visited property is equal to false, so make it true. Collect the adjacent vertices of A. They are C and D. Pop D. Since its visited property false, make it visited property true. Collect the adjacent vertices G and T. Stack is not empty. Pop T. Make its visited property true. It has no adjacent nodes, so give up. Pop the next. It is G. Make its visited property true. It has no adjacent nodes. I'll leave it. Pop C. Make it visited property true. C has no adjacent nodes, so leave it. Now the stack is empty. The iteration terminates. So we will be visiting the nodes in the order. First S, then we have pop B, then we have pop F, then we have pop E, then we have pop A out, then we have popped D, then we have popped T, then the popped item is G, then C. In this order we have visited the vertices. Okay, let us check the recursive one. Will it give the same sequence? So recursive DFS. Starting one is its visitor property is false. Make it visited. The adjacent vertices of S are A and B. Choose A. Make its visited property true. Then correct the adjacent vertices of A. Last we have selected B first. Okay. Let us start with the DFS with S. S is not visited. So make the visited property true. Collect the adjacent vertices of adjacent vertices of S. They are A and B. S is visited. Adjacent vertices of S are A and B. Pick B. Make it visited property true. We have visited B. Adjacent vertices of B are E and F. Pick F. Make it visited property true. F has no adjacent vertices, so return to B. B has one more adjacent vertex, it is E. So make it visited. E has no adjacent vertices, so return to B. All the adjacent vertices of B has been visited. So return to S. Okay, we have done with one adjacent vertex of S. One more remaining A. So come to A. Make its visited property true. Collect the adjacent vertices. They are C and D. Pick D. Make its visited property true. Collect the adjacent vertices. G. They are G and T. Select T. Make its visited property true. We have visited T. T has no adjacent vertices, so nothing to do there. Return to D. D has one more adjacent vertex, it is G. Make its visited property true. Then G has no adjacent vertices, return to D. We have done all with D. So return to A. One more adjacent vertex remains, it is C. Make its visited property true. C has no adjacent vertices, so nothing to do there. Return to A. We have visited all the adjacent vertices of A, so return to S. We have visited all the adjacent vertices of S, so return from the procedure. Okay, we got the sequence S, B, F, P, A, D, T, G, C. We got the same sequence with this iterative DFS. In iterative DFS, we use a stack to get the recursion. Then what about BFS? In BFS, we use a queue instead of stack. In BFS, we use a queue. And let us draw the tree again. We start the iterative BFS on yes. So put yes into queue. Then queue is not empty. Pop is out. Make it visitor property true. We have visited yes. And collect the adjacent vertices. They are A and B. Q is not empty. Pop, sorry, not pop, but A and Q. A, so we will become the front element. Previously this was front of the queue. Now this is the front of the queue. A is out. Make its visitor property true. Visiting A. Visiting A. Collect the adjacent vertices. They are C and D. They were not visited. Put them to Q. C and D. Pop B. Sorry, not pop B. DQB. C will become the front element now. B is not visited, so make B's visited property true. B visited. Then adjacent vertices of D are E and F. Put them to the Q. Now C is the front element. DQC. This will be new Q. C is not visited, so make its visited property true. The adjacent vertices of C, nothing. Pop the next item, sorry, DQ the next item. It is D. This will be the new Q. D is not visited. Make the visited property of D true. The adjacent vertices of D are G and T. Put G and T into the Q. Make okay. Then DQ the next item, that is E. This will be the new Q. F, G, T. D is not visited, so make the visited property E2 true. then he has no adjacent vertices. So DQ the next item, that is F. Visited property of F is false. Make its visited property true. F has no adjacent nodes. So DQ the next item, that is G. Make its visited property true. No adjacent vertices. So DQ the next item, that is T. It is not visited, so make its visited property true. It has no adjacent nodes, and this Q is empty now. We are terminating the iteration. Okay, in this order, BFS visit the nodes. You can see S is in the first level, A and B are in the next level. See this. A and B are in the next level, then C, D, E, F. They are in the same level, and last level is G and T. So BFS visit the nodes after completing the visit of all the nodes in one level. Here our task is finding an ST path using BFS. The Edmonds-Karp algorithm specifies the way of finding augmented path. So we will do BFS on the given graph, the given flow network. Then we will find the minimum augmented path. What we have to do is do BFS to find minimum augmented path. Do BFS to find the minimum augmented path. For this, given the flow and capacity values, put the weight of all edges equal to 1. Then the minimum augmented path will be the path with a minimum weight or minimum distance. So while doing BFS, you will be getting many augmented paths. So select the minimum weighted augmented path and form the residual graph. First you have to apply the algorithm on the given flow graph. You will be getting many augmented paths. Select the augmented path with minimum distance. Then construct the residual graph. Next you will be applying this algorithm on that residual graph. Find the minimum augmented path, and according to that path form the residual graph. Okay, this way you will be proceeding, and you can stop the iteration. You can stop the iteration if there are no more augmenting paths in the residual graph. And considering the backward edges, you can find the maximum flow from the final residual graph. Let us check an example. Consider this flow network. On this, we are applying Edmonds-Karp algorithm for finding the maximum flow. The first step is find the minimum augmented path using BFS. So we have to apply BFS on S. Let us start with S. So put S in the queue. The queue is not empty, so DQS. The adjacent vertices of S are 1 and 2. 1 and 2. That is, we can reach 1 from S and 2 from S. Q is not empty, so DQ1. Okay, then this will be the Q. Then adjacent vertices of 1 are 2 and T. So there is a path, 2 is already there in the queue, 1 to 2 a path is there, then 1 to T a path is there. So we will be putting T in the queue, 2 is already there. Then you will be dequeuing 2, which are the adjacent vertices of 2. They are T and 3. T is already there. 2 to T path exists. Then 3 is not in the queue, so put it in the queue. 2 to 3. Then you will be dequeuing T. This will be the queue. T has no adjacent vertices. Dequeue the next item, that is 3. Adjacent vertices of 3 are only T, that is 3 to T is the edge. Next you will be dequeuing T. Now the queue is empty. You can stop BFS. So what are the paths you are getting? First one, S21. Then you can move to 1 to 2 or 1 to T. So this will be the second path. S21, then 1 to 2 or S21, 1 to T. Then 2 to where you go? You can move to T from this. S21, 1 to 2, 2 to T. We have reached T, so we got an ST path. Then is there any other paths? we can move from S to 2, then 2 to T, or 2 to 3, then 3 to T. That is S to 2, then 2 to 3, then 3 to T. So you are getting 4 augmenting paths. Then what is the length of this? Because you have to you have to select the minimum augmenting path. And how do we find the minimum augmenting path? So give up the flow and capacity values. Assume the weight of every edge equal to 1. Then what is the length or weight of the augmenting path or ST path 1? How many edges are there? 3 edges, S21, 122, 22T. So length will be 3, or weight of that path will be 3. Then what about 2? There are 2 edges from S to T. You have to travel through 2 edges to reach T from S. So it will be 2. Here also length will be 2. The last one length will be, you have to travel through 1, 2, 3 edges. Okay. So you got 2 ST paths with minimum length. You can pick any of this. Let us select S2, 2 and 2 to T. This one. Let us pick this one. S2, 2 and 2 to T. This is one of the minimum length augmented path. Okay, next we have to construct the residual graph. Then what is the bottleneck capacity? We have selected S2, 2, 2 to T with bottleneck 3. Next we will be constructing the residual graph. The remaining capacity will be 12. This will be, the reverse edge will be 3. Then here 2 to T, it is over, its capacity is hosted. This will be the residual graph. Okay, here you have 2 minimum augmenting paths, and we have picked S2, 2 to T. You can take S2, 1 and 1 to T directly from here. We have 2 minimum distance augmenting paths. We have selected one, S2, 2 to T. The next minimum distance augmenting path was S2, 1 and 1 to T. Let us consider that also. S to 1 and 1 to T. What is the bottleneck? It is 1 to S to 1 1 to T. Bottleneck is 8. Bottleneck 8. Then next let us consider the residual graph. Here we are considering S to 1 1 to T with bottleneck 8. Bottleneck is 1 to T. This edge is S constant. Flow from S to T is 8. Sorry, S to 1 is flow from S to 1 is 8 and the remaining capacity is 12. Okay, this is the current residual graph. We will be doing BFS again for finding the minimum shortest path. So put the source S in the queue, take it out, enqueue that. Adjacent vertices are 1 and 2, S to 1, S to 2, then take 1 out. Adjacent vertices of 1 is 2 now. 2 is already there. So 1 to 2 a path exists. DQ2 adjacent vertices of 2 is only 3. 2, 2, 3. Then take 3 out. Adjacent vertices of 3, it is T only. 3 to T. Take T out. No adjacent vertices, Q is empty. So how many paths you are getting here? S to 1, then 1 to 2, 2 to 3, 3 to T. Another path is S to 2, 2 to 3, 3 to T. These two paths you are getting. What are the shortest? In the first one, 1, 2, 3, 4, 4 edges. The second one, only 3 edges. S to 2, 2 to 3 and 3 to T. So you will be picking this one. This will be the shortest ST path. What is the bottleneck? So you will be selecting S to 2, 2 to 3, 3 to T with bottleneck S to 2, 2 to 3, 3 to T. Bottleneck is 10. Let us draw the residual graph. So this edge it is reversed because its capacity is exhausted. Then here 32T 10, remaining capacity is 2 only. And what about S2 2? We have augmented a flow 10. So this will become 13, and the remaining flow will be 2 only. So S22, 223, 32T. Then try to find more augmenting paths. Is it possible? 3 to T, one path exists. The other paths to T, they are exhausted. But you can't reach 3 because the edge is exhausted. Then another one is S21, 1 to 2, but you can't reach 2 to T. Then S22, you can't reach T. So here no more paths exist. Then consider the reverse edge, backward edges. The maximum flow will be 8 plus 13. Consider this T. The reverse edges are 8 plus 3 plus 10. So the maximum flow will be 21.